All this one is what we refer to as derived units. The same thing for speed. They have the same units. Meter per seconds, they have the same units. Take care of that. This is the summary of fundamental quantities and derived quantities. I want to stop here now, and we are going to consider some questions that are frequently asked by this body. This body, JAMB. We are going to consider some questions and the way they ask questions from these topics, so that if you come across any of them, you won't miss it. This one should be a bonus for you. It should be a bonus for you. So let's see the first question. The first question said, the internationally agreed system of units, that is SI units, for physical measurement are. Please, I want you to understand this question very well. It's a common question that it can also come out during your own time, because we have been seeing it from time to time. It has been a repeated question. So please take note of this. The internationally agreed system of units for physical measurement are, we have the options there. Option A, we have 3 of them given. Millimeter, comma, we have the feet, comma, seconds. For option B, we have gram, comma, meter, comma, seconds. For option C, we have a kilogram, comma, meter, and then seconds. Then for option D, we have centimeter, comma, gram, comma, and seconds. Those are the options. So we are going to see which one is the system of units that is being agreed upon internationally for physical measurements. I personally put this one for you. This is the answer, which is kilogram, meter, and seconds. And if you look at this thing very well, this one is the basics that form our physical quantities, that is the fundamental quantities. These 3 are very important: our mass, length, and time. So all the fundamental measurements in terms of quantities depend on these 3 quantities. Please take note of that. If you see something like that in your exam, that is what is being expected from you. Question number 2. Which of the following is not a fundamental SI unit? For A, we have meter. For B, we have ampere. For C, we have Kelvin. For D, we have seconds. For E, we have radian. We have 5 options. Let's take it one by one. Meter is the unit of length. It's a fundamental quantity. What about ampere? Is the unit of current, which is also a fundamental quantity. For Kelvin, it's a unit of temperature, which is also a fundamental quantity. What about seconds? It's the unit of time, which is also a fundamental quantity. But if you check all what I listed for you, the examples of fundamental quantities, radian is not there. That means radian is not a fundamental. Right? As in radian, which is the unit of an angle, okay, is not among them. So radian is the answer for this question. Radian, which is option E. Let's consider question number 3. Which of the following is a fundamental unit? You can see the way they are asking their questions. It's almost the same. It's almost the same thing in different ways. Okay. Which of the following is a fundamental unit? Option A, Newton. Option B, watts. Option C, joule. Option D, seconds. Let me remind you, something is very important in this topic. You must be able to recognize the unit of each of the quantities. Now we are having Newton. Newton is the unit of force. And you know, force is a derived quantity. We also have watts. Watt is the unit of power, and power is a derived quantity. What about joule? Joule is the unit of work, and work is a fundamental. But what about the fourth option, which is seconds? Seconds is the unit of time. Therefore, times is a fundamental quantity. And the question says, which of the following is a fundamental unit? The right option there is option D, which is seconds. And seconds is the unit of what? Time. Please take note of that, which is very important. Question number 4. That one will now take us to what we call dimension. Dimension. We have something we call dimension. This one will not be new to you. Dimension of physical quantities. Before we can write dimension of any of our physical quantities, either fundamental quantities or derived quantities, we use all our fundamental quantities to write the dimension of other quantities. And we have 3 quantities that are very, very important: mass, time, and length. What is the dimension of mass? Just write capital M. What is the dimension of time? Capital T. Dimension of length? Capital L. As simple as that. Once you can master this, all the other ones are simple things. Okay? From this knowledge you have just gained, I'm just reminding you what you have known before. Let's now consider some quantities. How do we write their dimension? See, this is very, very important. There's no way they will not ask you a question on dimension. You can't escape it. And if you see anything on dimension, it should be a bonus mark for you. So, let's see the following. So, this one will take me to question number 4. That says, write the dimension of the following quantities. I have tried to check past questions for you, and I have combined some quantities together. So we are going to consider some of them and how to write their dimension. So let's take the first one, work. This is common. If you have been checking past questions, you will see something like this. It's so common. Work. Before you can write the dimension of work, you can use 2 methods to do that. It's either you use the formula of work. Work is force times distance. That is the combination of 2 derived quantities that give us work. We have force, we have distance. But you know, force itself has its own formula, because force is the product of mass and acceleration, which means we have to know the dimension of force first before you can write the dimension of work. Okay, let's see that. As I've told you, the dimension of mass is just capital M. But if you look at the next quantity for that gives us force, we also have acceleration. Acceleration itself also has its own. You have to know but for acceleration, okay, let me take it like this. Just be following me. Acceleration, as I have told you, is velocity over time. And velocity itself is distance over time. Okay? So to write the dimension of acceleration, then we are going to have, if velocity is distance over time, then we are going to have Lt minus 1. You may be wondering, how do we get this? Let me split it for you. Velocity is distance over time. For distance, this can be related to length. Whenever you see anything like length, breadth, height, whenever you see something like distance, displacements, All these, they have the same dimension, which is L. Because length, breadth, height, distance, displacement, all these, they have the same dimension. Whenever you see them like this, their dimension is L. So distance, for distance, dimension is L, as you can see. For time is capital T. So if you try to combine this together mathematically, this one will give you L T to the power minus 1. If you take this one, the power here, the power on the top of this capital T is 1. If it move up, you remember your indices, okay? You are going to have raised to the power minus 1. And this one alone is for velocity. It's for velocity. Okay? For acceleration now, it is now velocity, which is this, divided by time, which is another capital T. The power here is 1. Put this together. L T minus 1. Then times another minus 1. This is 1. By the time it moves up, you have another minus 1. All these numbers should not be new to you. Then raised to the power what? Minus 2. This one we are having alone is for acceleration. Remember, this is where we are going. I know you know how this thing, I'm only trying to remind you, okay? This is the dimension for acceleration, okay? But the force itself